Now let's look at arterial intersection. Look at this intersection. Arterial is very different from the motorways. Whatever we have been discussing so far was on motorways, where not different approaches are going to conflict each other. But here on this intersection, you can see there are different approaches, and there can be a significant conflict among these approaches. For instance, if I look at this through movement, that through movement is having a conflict with this right turner. So there is a possibility of an accident at this point. Similarly, another through movement here, it might be going this way, another conflict point. A right turner who wants to go this way, another conflict point. Left turner, and another conflict point, and so on. So there are multiple conflict points where the accidents can happen. So these are the movements where if you allow them going together, they can lead to an accident if there is a significant demand for those ones. And same thing you can draw for other movements also. So you want to, and in fact, it's always, if you look here, there are multiple road users. This is from Queensland. You have a cyclist, you have an e-scooter, you have cars, you have ambulance. Multiple road users are there, and they are different conflict points. So because of these, you basically decide the right of movement for certain approaches at any given time. So at any given time, only some of the approaches can use this space, and that leads to the signal control. It can be manually done, like a policeman standing at the intersection decides who is allowed to enter, or we can do it in more advanced ways by putting traffic signals, and then the drivers understand what is green, what is red, what is yellow, and we all know that, right? What is red, green, and yellow. And there are certain design specifications regarding how many lanterns to put, where to put the lanterns, how high they should be. Australia is very conservative. They have far higher requirement than any other place. For example, a driver might have to, you have one lantern here, you have other ones. So you have anywhere in that queue, you should be able to see the signal. That's the requirement which is there. You have a traffic signal controller cabinet along the side, which is the one which is controlling the traffic signals. Signals has been there for long. It's not something which has just come. The first use was in 1868 itself, when basically there were horse-drawn carriages moving along the intersection. So at that time they started using this one. In Queensland, they are using for 1936. We have more than 2,000 plus signals in the city of Brisbane. Now these signals have to be optimized, and in a specific city council, there might be maybe one or two engineers who have to do this job. So engineer might have thousands of intersections under his or her action or job portfolio to handle. It's a very complicated process, right? There's a systematic way of doing it, but there is always a workforce challenge attached to it. There are some definitions like movement, which is each separated traffic flow characterized by its direction. These are movements like through movement, left movement, the right movement, which I believe you understand when I use the word movement. We can group the compatible movements like phases to define the phase. I can have one phase like this, second phase, third phase, fourth phase. I can have different phases with the objective that the phases should not, they should be safe. They should be compatible with each other. They should not lead to accidents. That's the requirement. I can have 16 phases, I can have 4 phases, I can have whatever number is needed to actually make it safe. Sorry. Now, at any given point of time, the signal design question is which movement to be allowed and which is not to be allowed to enter the intersection. That's the first question. how long they should be allowed. And obviously to do that, you have some optimization objectives in mind. You want to minimize the delay, and you should always have a safe transition. So let's have a look. Let's say for this intersection, I have defined my 4 phases. So first thing I have done is, these are the groups I'm going to allow at any given time together. I can allow them. And I've defined the sequence also, for instance. Say I'm going to give a green to this approach. So x-axis is the time here now. And y-axis is just an order. That's all. It's not space. I'm going to give a green for that much time to this approach. Then after this, I will not straight away jump to another approach and give a green to that one. I might like to give some warning to this person. Look, the green is about to end. That's the yellow time I'm going to specify. Then I'm going to give a green to the red to the other approach. Should I jump to the red straight away? Or should I make this, should I start giving green to the other approach straight away? No. In fact, when we are giving green to this one, the others are red, by the way, right? Now, I want to now give a green to this one. I will start giving green to that guy, but there is some time I will make sure that all the other ones are red. I will not let anybody enter the intersection, and that I am doing it with it for clearance, for safety. I do not want to have an accident, because I know that there will be some stupid people on the road who are going to just enter the intersection at the end of this. And I want to make sure when I'm giving a green to the next approach, the signal is totally free of other vehicles. That's why you have an all red phase here. And then obviously you're going to repeat, when I'm going to give a green to this one, others should be red. Is that okay? And then you keep on repeating this cycle. Yeah. And you've done the green for all. And after this, I will go back to this and keep on repeating it. You can express it in the form of a cycle also. You can think of this repetition happening continuously. You have a green time, you have an all yellow time, you have an all red time, then again a green time, yellow and all red time, and so on. Just keep on doing it. Now, why do we need a yellow time? And how long yellow do we need? Yellow time is after the green. So during the yellow time, when you're giving a yellow, you are basically letting these guys on it. You're not letting others to enter. And these guys don't even know that the other one's having a yellow. So why do you need a yellow time, and how long? I've already mentioned that you need the yellow time so that you are warning the drivers that it's about to end. You should stop, right? But how long yellow you should be giving? Yes, speed is one. What else will be there? Oh, that is for the, yeah, okay. That's okay, good. During the yellow time, yes. So basically, when you are driving and you see a yellow, depending on how far you are from intersection, either you will be able to clear the intersection, or you will not be able to clear the intersection if you want to clear, right? Or you will be able to stop, or you will not be able to stop, depending on how close you are to the intersection. If I am driving, system turns yellow, and I'm at a one speed, and I'm just few meters away from the intersection, and I decide to stop. I apply brakes, I may not be able to stop because I'm so close. I will just stop in the intersection. Or I'm so far away and my current speed, I thought I have to clear the intersection. And with my current speed, I basically hit the intersection when the system was total all red. So there is always a dilemma, right? When you see the yellow, you're always thinking whether I should stop or I should not stop. And depending on, you make a judgment. So yellow time should be long enough so that drivers are able to stop if they are close by, or if they are a certain distance, or they're able to clear the intersection. So basically, there is a concept called as a dilemma zone. You want to minimize that. So let's have a look on this. Suppose this is a zone, let's call it zone here. That's the vehicle driving at a speed V0. Yeah, at a speed V0, this car is moving. Now, if the yellow hits with this speed, if the vehicle is traveling at a speed V0 and can have a maximum deacceleration of A, the maximum it can deaccelerate, stop, right? With that speed, if the driver decides to stop, for instance, let's say the reaction time is TR, is going to react after a certain time interval, maybe 1 second, 2 seconds, for instance. Yellow happens after 1 second. Within that 1 second, driver has already moved by that much distance. Plus, we know that V square is equal to U square plus twice AS. So that's the distance the driver is going to move further to stop, right? But that is the distance. X is the distance. If the driver reaction time is this much, then the distance the vehicle can travel if decided to stop is given by that much. So from here, if you are x1 distance apart, right, you need actually that much distance to stop. So technically, if you are within this x1 region, you may not be able to stop because you have a length here, you might somewhere stop here. Yeah. So x1 is the region where you cannot stop if you decide to stop, if you decide to apply your brakes. Are you okay with this? So if you are in the x1, it's better you just try to clear the intersection. Where I have already mentioned, this one is the distance that you will travel for your reaction time, and this is the distance you need to have a complete stop. So x1 is the minimum distance from the intersection for which a vehicle traveling at a speed V0 during a yellow time interval cannot go through the intersection without accelerating. If you are somewhere above this, you should be able to stop. Only in this region you can't stop. Within the yellow time, we specify. Are you fine with this? Let's do another one. Here, we are saying that x2 is the distance within which a vehicle traveling at speed V0 during the yellow interval cannot stop before encroaching the intersection. So, if you were, let's say, here, and if you are somewhere here in this region and you decide to go with your current speed, you will not be able to actually clear the intersection within the yellow time. If you are somewhere here, right? If you are within this, you should be able to go. So we are calling another distance x2 here. What that is? The speed at which you are traveling multiplied by the yellow time. So at the speed v into yellow time is the distance you can travel in yellow time plus how do I say this one? Actually, in the yellow time, you should be traveling all the way from here to there. So your front bumper should hit there, right? So that is this x2 plus w plus l should be the distance you should be traveling in the yellow time. Even if you are able to enter the intersection in the yellow time and you are somewhere in this intersection, you have actually broken the law. You're fine, but you have risky. Well, generally by law, you should never enter the intersection when the signal is red. So even under the yellow you have entered, you should not be fined. But you have to clear the whole intersection so that there is no accident. So this is, if you rearrange this term, you say x2 is basically given by that one. So speed multiplied by yellow time is the distance that should be x2 plus w plus l, right? So if you are somewhere here and you decide to continue, you will not be able to clear the whole intersection. You will be somewhere in between. So technically somewhere here you should not continue. Now if you look at this thing together, if there is an overlap happening in these two regions, here you can't stop without having a very harsh deacceleration. Here you can't go. So if any such region exists, you are in the dilemma. You don't want to have that. You want these to be totally separate. Yes, that's what we call as a dilemma zone. So you do not want to have a dilemma zone there. And that's what is going to be defined by the yellow time. So what you're saying is, to avoid dilemma zone, this x2 should be much larger than x1. If they are apart, this overlap will never happen. So x2 should be much larger than x1. Rearrange your equation. You find that your yellow time should be more than certain value. Yes? So yellow time depends on, yes, you are right, it depends on the speed, the design speed. It depends on the width of your intersection. It also depends on whatever is the effective length you are thinking about. So on a specific corridor near to an industrial area, should you be giving more yellow time or less yellow time compared to a corridor or intersection which is near to a residential area? If you are a traffic engineer, you are designing a yellow time for a specific intersection. One of them is very close to an industrial area. Other one is very close to a residential area. Which one should have more yellow time? And why? Residential should have more? Why? Commercial should have more? Why? You never want to be in that zone. You never want to have x1 and x2 overlapping. You always want to have x2 here, x1 there. Okay, but I'm not talking about pedestrian here. In fact, I'm not going to talk pedestrian at all right now, right? I use the word number 3, width of the intersection plus length of the vehicles. Just think from the length. Industrial zone might have heavy vehicles, right? So it might take more time for them to clear all those things. So you might, you have to consider multiple factors, right? It's not that I do not know which one, because it depends. If you have a larger intersection because you want to have a heavy vehicles to move around, you have a larger heavy vehicle, definitely you need to give them more yellow time. It takes more time for them to actually clear. So, and whereas a residential area, you have cars, the length are small, intersection widths are small, chances are that you are happy with the lower yellow time. Yeah. So now I have defined the yellow time, and which is different for different intersections. It's not the same. And that depends on your design parameters. So whenever you're going to design traffic signals, first thing you have to understand what that intersection is. You should know the geometry of the intersection. You should know who are the end users of that intersection. And then you start designing it. So I have defined my yellow time. That is one thing I have defined now. Now you have yellow, you have red, you have all red. I don't know why I copy the same slide here, but I wanted to show that this part, yellow and all red, that the one that you see here, this is a clearance time that you specify. Well, you assume that the drivers are going to use the yellow time, and they will be using it. They're not going to be just stopping the moment they see the yellow. They'll be using it. But drivers should not use the all red time. And this is a clearance time you give to go from one signal to another signal. All red time is pretty simple, that you are giving all red time so that any vehicle which just enters the intersection at the start of the red all should be able to clear that intersection. So it is length plus width divided by the speed that you have designed. Again, you might have different design speeds. I can have a different design speed for through. I can have a different design speed for left and right. Again, totally your engineering judgment or engineering value you specify. But it again depends on the road geometry. All phases are red. Nobody is allowed to enter. That's the one I was trying to explain in this one. That when you give a green to this, all the others were red. But when you're giving a green to this guy, you do not jump green, this excess time. You don't give green straight away. You have certain time where you give red to all of them. That's why we are calling it all red. Nobody is allowed to enter. which you might not know when you are a driver, because you might be driving here. For you, it's green or red. For you, either this or that. But technically, there is a certain time period when everybody is observing the red. That's what I said. It depends on the side by side. So it should be length plus width by speed. It may be 3 seconds, 4 seconds, depending on the bigger the intersection, the larger the intersection, more is all that time. But this is the time you are going to lose. Yeah. So you want to minimize it, but you want to add it for the safety. This is for the safety reason. Oh, there's the speed of the road. You know that. I know my speed. I said I'm going to have this as a speed of 60, for example, or 40. That's the speed of the road. That's the speed for which you are designing your intersection. Yeah. Red for 1 minute for all the approaches? For all? 1 minute. Why? I 1 minute red for all the approaches. I'm surprised. Okay, there must be something else happening there, because then that is not all right. That is an all right for some other purpose. Here the all right is to avoid to make sure that the signal, so the intersection is empty when you're letting the next guys to enter in. Hmm. They can't wait. I mean, people will not wait. The frustration is there. Yeah.
Even pedestrians, two pedestrian movement are there at that time. Because manually operated signal intersections are there. Maybe they.
Okay. I've seen. I mean, couple of years back, when I was in my hometown Lucknow, I've seen that one of the intersections, policeman was manually changing the signal timings. Yes, they have signals, which is good. That now the police, because the moment you put a policeman at the stop at the center of the intersection, you're exposing him to so much pollution. It's not good for the health of the person standing there. So it is away, but they are manually changing it. But they're slowly transitioning at that one. So I'm not aware of what's happening in Bangalore, but I mean, there should be some reason, hopefully, that they have done that way. But here I'm trying to talk about the general fundamentals, that this is what you need to do. You need to have an all red phase, definitely. In fact, the all red phase is quite interesting. You know, we have a new technology, not new technology, there's a new strategy that they've implemented in Queensland. We call it hold the red. Yes.
So let us assume it is a major, like W of which you had shown.
Yeah.
The minor road which is coming from the perpendicular, if the width is bit less compared to the other,
yeah,
then all right.
Then all red. See, then you have to think like this. If this is a major one, the all red at this time is to make sure that this is clear, right? So you're not letting anyone to enter. This might have one all red value. But if you are looking at the minor, for example, this is a minor one, right? So when you have given a green to this one, at that moment you can reduce the all red for that one. So all red at this time can be reduced, right? So it is an all red attached to the green which was served just beforehand. It can be done that way also. You can say for each phase afterwards, this is all red I'm going to give. It can be done in theory. In practice, it is done or not. It depends on your kind of controller you have, how much flexibility that software has to do that one in the real world. Yes, in theory it can be done, and it should be done that way, depending on your geometry. Yeah. It's a very good question you have asked. So all red is not all red fixed for the whole one. It is an all red with attached to a specific approach, a specific green. Yellow attached to a specific green. Now I was talking about the other all red is they have a they have a new technology called hold the red. So hold the red means they have a radar based system attached at further upstream. So let's say this is an approach, that's the intersection. They have a system attached here. This system is observing the speed of the vehicle, and system try to detect or make some chance. Okay, this vehicle is approaching at a higher speed. It's highly unlikely that this vehicle uh, uh, is going to have a red light running. It's going to enter the intersection when the system is red. So what this technology is doing is it is extending the all red all of a sudden for that phase. So they use the word hold the red, means hold your all red for a longer time interval, right? And it takes the image also, and the bill goes to the guy that you have done the red light violation. Because you're not supposed to enter the intersection at this time. If you are the guy traveling here, you can enter the intersection at yellow, but your back bumper or the back tire of the car should not leave the stop line when you are here. If it leaves, you have the red light violation. I don't know, maybe you have 3 or 4 demerit points, and you might have $300 or $400 fine. Yeah, but okay, yeah, oh yeah, yeah, okay, okay, good to know. I might see it. I might go and see it on Sunday. That's good. I mean, so these systems are there. Now here I was talking about the green, red, and all red time. Okay, you understand? You understand the concept of all red, because all red has been said. There is all red. Like if I show you the way I show you the circle, but here that all red is again assigned to a specific phase. So it's an all red, green, and so on. Now the next step is I have defined my yellow time. I have defined my red time, which is associated with the specific phase. Okay, I have defined that. So at least I know these yellows and reds. First step I have done was I defined my phases A, B, C, and D. Now let's call them A, B, C, and D for the sake of discussion. And I know these yellows and red. When I'm going from A to B, that's the amount of yellow red I will give. When I go from B to C, that's the amount, and so on. I have defined that. Now I have to define how long this cycle should be, and among that cycle, how much green should be. So I want to define how big my
Mr. Twinkle.
is there. Yes.
I just have a question here.
Yeah.
So is this how this green, amber, and all red and followed in Australia, or is it like anywhere?
So I am talking about a phase-based system. So this is phase. Yes, this is basically the general theory behind how do you define the signal timings, and for all the like phase-based system, this is how it is followed.
But I just want to share one example. See, yeah. I worked on this videographic analysis, like where I'll be getting the signal timings for an intersection.
Yes.
And I've also gone through this signal control specifications document from where I have to get the timings. So there I've observed, generally it is of UK ones. So the moment the amber time stops, the green for the other approaches or another stages will automatically start. So, and I do agree there is something called all red as well, but it is mostly being used at some points where pedestrian movements will be more. So then they'll be going for all red and stopping all the approach movements, and then they'll go for pedestrian movements for that.
Yeah.
So this is something different.
Yeah. So what you're talking is basically, yes, this is possible. There are multiple variations. There are overlapping phases. So if you expect that there is a less demand, like for example, this is a major road and a minor road, and there is a very less demand for the minor, you can skip the all red also. It is possible. It is possible. But in terms of theory, this is how you define, and that's why I was saying your red and green and yellow time is specified for the phase and the transitioning to the next one. So yeah, it is possible.
Yeah, so it is not mandatory to go for all red every time after one
Uh,
approach
it
arms
depends
takes
on the
place.
jurisdiction. In Queensland, to my knowledge, it is mandatory. So it all
Oh,
depends on how much risk that agency or that jurisdiction is taking. Yeah.
how long will it be? It's based on the calculations that you have shown
I mean,
previously.
it can, like I just mentioned, that it can be, like in theory it is based on the width of the road and the length of the vehicle, but you can specify maybe 3 seconds, 4 seconds can be the all right time, or maybe
Yeah. Thank you, sir.
even 2 seconds can be the all right time. So again, these are at the end of the day the the parameters specified by the engineer, subject to the constraints or subject to the policy of that jurisdiction. Thanks, thanks for raising
Yeah.
that. Yeah,
Yeah. Thank you, sir.
yeah.
changes in nearby nearby pathway.
Nearby pathway means
But in one roadway, the vehicle comes and the yellow light comes. Then after that, the nearby intersection, four intersection, right, pathway, and crosses nearby.
okay. You are saying that it just take another approach out. Okay. I mean that's what the driver is doing. So it has nothing to do with the control parameter design. It's possible. That's the driving behavior. A driver might have his or her own behavior of driving. So they enter the intersection. All of a sudden they decided to go left. That's a totally abrupt behavior of a driver. But when you're designing signals, you're not considering those kind of behaviors. I mean, you don't want. I mean, those are the behavior of the driver itself. So you are assuming that okay, traffic is flowing in a certain manner, and this is the amount of green and red I should be giving to the approach. Yeah.
For example, if this is the intersection ABCD and then the traffic is on A side and there is no traffic on B side, should we wait for the completer side?
No, 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 no. We don't have to wait for that way. This is I'm just right now. I'm just talking about a simple theory. In the practice, you can skip the phases also. You can skip them. You define the minimum green, maximum green for each approach. If there's no demand, you can skip the phase also. It's not mandatory to go in this order only, but this is a process you specify to define your green time and red time. We're talking about how the theory works, and the theory will help you to optimize what should be the minimum and the maximum green I'm going to give to that approach. And once I've given that, and when I'm implementing it, I will figure out, okay, look, this is a major approach, that's a minor approach. If there's no demand, you can skip that phase. That can be skipped.
Use sensors to identify there is no traffic.
Um, so basically, it all, like generally you are using loop detectors, and there are different ways of identifying that. Like the one I showed you for the Switzerland one, they had a long fuse detector. If there is no occupancy happening, you say there is no demand, cut it off. Other one is you might have a slightly upstream detector, which is observing the headways, and then there's a counter. The amount of unused green is, or the headways, unused headways are actually quite large. The headways are quite large, cut it off. So these are the certain rules that the controller might have to actually make the early cutoff. So those are based on basically mostly the loops, or it can be based on even the other technology also. But they are totally considering how many vehicles, like the headway between the vehicles at that time. Yeah. Sorry.
Loss in the green time because the spin like the gradient in
Mhm.
like the intersection was there. So in that scenario, that time it will be there. So Q time it will be
Mhm.
right.
Mhm.
And suddenly green might come in that moment. Mostly it cannot feel in the upstream.
Mhm.
So at that time, so some seconds it has been lost
So you're saying that when the signal turns from red to green, the vehicle don't enter straight away, there is a loss happening. I'm coming to that. Yeah, coming to that. Yeah. So the next step is, maybe I would like to define how big should this I would say pie should be, or right, how big the circle should be. So for that, I want to define my optimal cycle time. Again, there are different ways of doing it. I'm just trying to tell you a simple way of it. Webster did some kind of lot of simulations long time ago. Here, x-axis is the cycle length, y-axis is the delay at the intersection. Generally, the shape is something like this or some other form. And there is an optimal range of cycle time where the delay is minimum, right? And basically, generally, if your cycle is too short, if you're having a very short cycle length, then you are having very quite frequent changes happening, right? If cycle is too short, there are so many phase changes during an hour that the lost time due to these changes will be high compared to the unused green time. Like the lost time, generally the way you define, I will come to lost time again later on, but your all red and the yellow equivalent to that is the lost time in effect. So each, as the number of phases are increasing, your lost time is actually increasing also. So if you are, and this is the time, let's say this is 5 seconds. So 5 times 4, 20 seconds is your lost time, where you are not using the intersection much. And if your cycle time is, let's say 60 time, very small cycle time, 20 first 20 over 60 is the lost time. You're just losing that, unnecessarily that much time. So that's why you do not want to have a very low cycle time. But you also do not want to have very high cycle time. If your cycle time of, let's say, 5 minutes is too much, if you are stopping, and I've seen cycle time of 5 minutes in Delhi actually, 5 minutes, even higher than that. A very high cycle time, you are basically frustrated. So you don't want to have a very high cycle time. So there is an optimal cycle time that is basically what you are aiming for. And Webster gave an equation. It was optimization problem he did. He came up with an equation. The optimal cycle time is 1.5 L plus 5 divided by certain factor, which we will discuss later on. But technically what I'm saying is there is an optimal cycle time equation defined or considered by the specific jurisdiction. So different, I would say, procedures can be there, but there is an equation that will give you an optimal cycle time, where L is the lost time for all the phases. V by S is basically the design flow to saturation one, which I will discuss later on. But let's say you get the optimal cycle time. So that's the lost time thing you were talking about. I have a signal red, but when I go to the green, I will have here x-axis is the time, y-axis is the discharge rate. You won't have the 100% discharge straight away. Vehicles will be entering slowly, right, one by one. And after a certain maybe 4 or 5 vehicles, you will have a proper discharge rate. And vehicles will be utilizing some portion of your signal yellow time, right, also. Effectively, your display green is this much, but your effective green might be that much, the amount of utilized green. And we assume that both of them are equal in value. The amount you are losing in the beginning is the one you are gaining at the end. That makes the life easy for us. So your effective green time is your display green time plus intergreen time minus the lost time, the initial lost time. And if these two are equal, your effective green is same as the displayed green, but slight shift happening along the time axis. The yellow time plus all red time. Yeah. Let's take an example here. This is one of the intersections. I just want to show you like how the lost time. What do I mean by the lost time? Imagine this is the only video I had. There is a traffic moving, right? This first vehicle took some time after the green to enter. Second vehicle has, you can see the more headway, the third, fourth, and so on, and the queue is still there. So you in fact, this is not a perfect example because you are having a right turn, which has his own impact. Fortunately, we do not have too much queue for the through movement, so I only had this video to show to you. But I want to relate this with the headway. Let's say x-axis is the vehicle in the queue. If I go back to that video, first vehicle, see the first vehicle has entered, second hand has entered, and third. So the headway, imagine the headway here. The first vehicle has a higher headway from the start of the green and so on, and the headway starts. Ultimately, it will lead to a saturation on average. Maybe not in this video you are able to see that, but generally it is going to lead to a saturation. And that's what we call, this is the lost time that you are losing in the beginning, right? You might have observed, I don't know, like generally the headway between the first and the second vehicle is always larger compared to the other ones. Where when the first vehicle leaves, second vehicle leaves after a longer time. And generally when we are driving, if there are two lanes, and if there is a queue on this one, and if you are able to make yourself the first one here, you will always have sufficient gap to merge down the line because of the reaction time and because the times it takes for the vehicle. Because they are pretty much moving from 0 to the speed, but the other vehicles, they start a bit early, and by the time they reach the intersection, they are already in the speed that should be there. So the headway of the first and second vehicle is generally larger than the other headways down. And you can see here, this headway and the headway starts increasing. Yeah. Now this is a simplified example just to explain the critical flow ratio. Now, obviously, before you are designing the intersection, you should know how much demand is expected from various approaches, right? Either through survey or some other means. You should know how much, for what demand you are trying to optimize the signal timings. So for each of the approach here, let's say V is the volume. I've not discussed the saturation flow rate, but S is the saturation flow rate. How many of you know saturation flow rate? Everybody know that saturation flow rate? It is a rate at which the traffic will be entering the intersection when the signal is green, right? So which by the way is the inverse of this headway. So saturation flow rate is known to you. Let's say V1 is the demand for this through and left. V2 is the demand for this through and left. For this specific approach, if you go for V1 over S1, the volume over the saturation, the one which is maximum, right? V1 over S1 or V2 over S1, the one which is maximum is called that the critical flow ratio for that phase. So for this phase, the one having a higher flow over saturation is the one which I should definitely be looking at. So let's say this one is higher, this one is lower. I should definitely give enough green so that this one is flushed even if the other one Q has gone to 0. Yeah, that's why you look at the critical one. You do the same for B, C, and D. Once you know that volume or that volume to actually saturation flow rate ratio for each of the phases, the critical one, you know your cycle length. What you have to do is just distribute that cake in terms of how much volume is there. So what you do is you define the green based on the amount of critical flow to saturation I have plus amount for all the intersection. That's all. If let's say this one is, let's say 0.8, other ones are the summation of other one is some other value. So if 80% of that should go to A and other ones should get the other percentage, right? So this is the way you try to spread the, like this is the way you try to spread the cycle over the different different approaches. No, they have their own acyclic, and they have their own, the modified versions are there. So I'm not going into details of those ones. Equations can be different, but the concept is still the same, right? So acyclic delay equation is the one that they use instead of using the Webster delay equation. There might be slight modification in terms of the optimal cycle length compared to the practical cycle length. Some modifications will be there, but the concept is still the same from the phase perspective, from the phasing perspective, right? So to design the signal, first thing you have to do is look at the roadway condition, identify the number of lanes, the width, length, etc. Like you should know that what you are designing for. Know your traffic. See, I have discussed in a very simplified manner. I just said the volume, but actually it's not the volume. It is basically expressed in passenger car unit also. It's about of traffic, right? Whether you have a cars or the buses, etc. Those things have to be considered. So the traffic and the vehicle composition should be known to you. Your saturation flow rate is also not a straightforward value. It depends on number of things. Whether I have what kind of gradient I have, right? So it depends on the road geometry, left turners, right turners, through turners, the lane widths define the saturation flow rate, and there are manuals and procedures to get that. But once you get the saturation flow rate, you know your volume. You can know the volume, the critical flow to volume ratio, or volume to the saturation flow rate ratio. Oh, thank you. So the design process is decide the phase sequence, identify the intergreen time, estimate the cycle length, grade the green splitting. I've not discussed about the pedestrian requirement for the sake of simplicity, but amount of green you're going to give to an approach. For example, if I look at this phase might be, you might like to have some green if they are going, for example, if they're going this way and that way, through, no, this is not the good one. I said they are going this way, you might have some kind of a green time given to some approaches allocated with that one. And based on the width of the road, based on the speed by which the pedestrians are walking, you will have a minimum green time so that the pedestrians are served properly when you are giving the green to this approach. Yeah. So that is also an additional constraint you're going to add. Yes, if the pedestrian movement is there, you can't skip. You have to have a pedestrian phase, right? If there is a lot of pedestrian movement, you can have a separate pedestrian phase assigned to it also. So there's no set. These are steps which are there, but your intersection complexity defines the way you're going to define that parameters. Your engineering judgment depends on the kind of characteristics that your intersection has, right? Although these steps are there, right? Even after you have defined the signal timing, you have to evaluate the performance, that how much expected delay is there, what is the expected level of service for various approaches, and if the performance is not good, you will go back and fine tune it. So this whole process is repeated, and it need not to be in the order which we are saying here. That depends on the way you are designing it.
Can we come out with some different loss if it's happening because of waiting period and
Yes, that's what we say, performance evaluation. At the end of the whole process, see, like for example, there is a delay equation. Maybe it's a Webster delay equation or actually delay equation, or you can use some other modeling tool, let's say Sidra. That will give you the amount of delay for all the approaches after your signals has been optimized, and that delay you see whether it is acceptable or not.
then we can decide for short-term
Oh, we're not talking about flyover here. It's just about the.
after identifying the value that the delay too much is
Here, when you're designing your traffic signals, right, your volume is within certain range. If your demand is anyway very high, then you can't do anything, right? Your volume, the signal should not be overly saturated. I can give green. Imagine I can give green to a specific approach to a certain amount of to a certain limit, as green to some other approach. But let's say if my volume to saturation ratio is very high for all of them, I can't do anything. No matter whatever I use, there will be system is oversaturated. These things, you are doing it in a way so that the system is not above the capacity of the intersection. And why it is important to optimize? We all know that, traffic signal, everybody is affected by traffic signals, no matter whomsoever that person is. Whether it's a personal vehicle, like you might be a e-scooter guy, you are impacted by traffic signal. Cyclists, you are impacted by traffic signal. Pedestrians, you are impacted by traffic signal. The public transport, sorry, the heavy vehicle is impacted by traffic signal. Your emergency vehicle is impacted by traffic signal. Everybody is impacted by traffic signal. So you have to think of ways to optimize it. Delay. Yeah. At the isolated intersection, if you're only looking at one intersection, it doesn't matter much. But if you're looking at a group of intersections, it will matter a lot. The way you coordinate one with another one. So order of the phases only for one intersection, you're only looking at one, right? Not worrying about the other ones. Based on the way the demand is approaching. So this is very complex thing. It's not the way the demand approaches here depends on the way the upstream intersection is defined, right? So if you try to coordinate these two, that when the traffic is approaching here, that's the time I should be giving green to this one. Then obviously the order is mattering, will make a big change. But the phases, the way you define the phases matters a lot. Phase definition matters a lot. I mean, I have chosen very simple example here. The phase design can be far more complex than this. You can have an overlapping phases between the two. I can have, through left and I can have, 3-1 left, multiple combinations. Phases can overlap each other. Then I think by doing so, when you're actually overlapping the phases, actually, one way you can get rid of the all red over the intersection is looking at the totally, not get rid, but basically minimize the all red requirement is when you are looking at a combination where you move from one phase to another phase, the transition is happening in such a way that basically you do not need to have this all red in there. Like we call that as a movement-based approach. This is the phase-based approach. I will discuss about that. In the case of movement-based approach, you try to utilize the intersection in such a way that you go from one movement to another movement with as much overlap as possible. Yeah. I think we can stop here. I will just show you actually, one video and then we stop. I mean, basically, it's about advantages of a poorly located intersection compared to advantages of a properly located and operated intersection compared to when you're not doing it properly. This is what I use to teach the high school kids actually, where we invite high school kids at QUT. Just for them, there are two separate control measures in simulation. One and both of them are having the same amount of demands, exactly the same demand. I've not done any change in that demand, but two separate ways of controlling. Right here, the order of the phases are different. You can easily see that one of the control how it is performing compared to the other one. Two different ways. I think the phase combis are different, but there's no change in the demand at all. So one of them is not performing that well, whereas the other one is far more optimized. And that's the reason why you need to actually optimize the signal timings better, or you really need to work on the signal timing optimization. Yeah. So it's almost close to 4:20, so we can take a break for 2 minutes. Then we jump on the tutorial section and we can finish by 5 o'clock. Yeah. Good. Any further question from the online audience? If you have energy, start looking at this question, start solving it. This is the RAM metering one, very similar to what we have discussed in the class, but slightly changed also. So here we have a linear algorithm, right? We are saying that assume that regulatory uh, regulator parameter 75 vehicles per hour, desired occupancy is 28% of a downstream detector, arrival flow, the metering rate for the last time interval was 900 vehicles per hour. Your current output occupancy is 29%. The on ramp has two lanes. So basically, it's not like the previous case. I only considered one lane. Now you have a two-lane on ramp, and you allow one vehicle per green per lane is admitted. So green time is 2 seconds. What should be the what should be the ramp signal red time? Or just tell me what should be the headway. Any answer? You have already solved this question in the class earlier. The only change I've done is I've given you two lanes instead of one lane. How much? 6 seconds of red. Okay. What is cycle time you get? Okay. So one lane. That's good. Yeah. More or less, yes. So basically, you have 900 in the last interval and 900 minus 75, whatever that value is, right? Should be your flow rate. What's that flow rate is? 825 should be the flow rate, right? And what should be the headway? If you have 825 as the 4.6. That's the headway you should have between the vehicle entering, right? But because you have two lanes, on average that's the headway. Because you have two lanes, you are letting two vehicles enter every time you turn a green, right? One vehicle per green per lane is there, because you will, if you have two lanes, you will let them through. It's not that you say go one first and the one. And if it is you're letting two, you have to increase your cycle time to twice that one, right? So if it was 4 point something, you have to make it 8 point something. Then after every 8 seconds or whatever, 8.36 seconds, whatever you get, you're letting two vehicles enter. So on average, it is 4 seconds per vehicle you are trying to enter. Does it make sense? No, the difference is now you have one vehicle per green per lane and you have two lanes of the on-ramp. So earlier I only talked about there is only one lane on-ramp. Now I'm saying that there are two lane on-ramp. The concept here is you have to increase the headway. You have to make it twice. Yeah. Or you can convert your flow rate to per lane, and then naturally you are going to get a headway per lane. So either way you should be fine. Are you fine with this? Yes or no? Next one is, if I change it further, I also specify a minimum RAM metering policy. I should not have any RAM metering less than 850. 850 is the minimum I'm going to specify. And now I have a new data set. So currently we have 1000 vehicles per hour in this current time interval. 28 is our desired occupancy. 32 is what I am observing. 75 vehicles per hour is the regulatory parameter. And again, one vehicle per green per lane is actually admitted. Find your cycle time or the green or the red time. Okay, I should have done that for the previous one. Sorry about this. So what previous case we are saying was, this is the equation you have, right? So it should be R K minus 1, by the way. So you had 900 vehicles per hour. Your KR was 75. Your occupancy is 28 minus 29. So that leads to 900 minus 75, right? That was 825. That's what you get. So 825 vehicles per hour is what you're expecting. That should be allowed to enter. Because you have two lanes, what you can do is, it means that 825 vehicles per hour, you convert that into 825 divided by 2 vehicles per hour per lane, right? You can do that. So from here you can find the headway. Headway should be 3600 divided by 825 by 2 seconds. That's the headway, right? So that is the headway you should be specifying, and that turns out to be 8 point something. 8.7, let's say, right? And you're going to give a green for 2 seconds. So this turns out to be 8.7 seconds. And because you're giving a green for 2 seconds, your red time should be 6.7 seconds, right? Okay, with this one. That's one way of looking at it. Other way, I was saying that even if you use 825, you get the headway from here. The headway turns out to be 4.35, right? So that headway is the headway at which you should be letting the traffic in. But because you have two vehicles, you double that headway. Because you have two lanes, which is same as you multiply that by 2. Sorry, I should have solved it. I was just, I was just putting on the, I was just discussing it in the air. Yeah. Yeah, I'll come. Are you okay with this? You're fine? Sure? Okay. Let's go to the next one then. That's the next one. This, yeah, 75. Yeah, I have to use 850. Yeah. Sorry? So what you're saying, in this particular case, what you're going to do is, the RK that you're going to use should be whatever you get from here, comma 850, whatever is the maximum of these. It cannot be less than 850. Yeah. You're getting, it has to be 850. You'll be using it at 850. Yeah. And from 850 you apply the same concept, right? 850, get the headway, make it twice, because don't forget that 2 lanes, right? Make it twice, or just convert 850 by 2 and get the headway. So there is always a minimum policy that you cannot go below that. Otherwise, this equation can shoot to any, and you will have a headway going very high value. So those are the things that you have to specify.
But the green time they have given is 2 seconds.
Because this is on ramp. This is a RAM meter, right? It's just a green flashing and then red holding. Because you are only allowed to enter once in each green. You just flash the green.
That is been fixed.
It's around 2 seconds, yes, more or less fixed. Yeah.
Maybe if you want more lesser storage, they will get frustrated.
Oh, that's why you put this one. In this particular case,
We fix the
yes, yeah. They've not trusted much, they'll just enter. Interestingly, RAM meeting, you never have a speed camera there. You don't, it is just that people just follow each other. If you go, somebody will honk from the back.
regulatory parameters.
That was this parameter, KR.
So practically,
Oh, that's the one you. I mean, basically, this is something that the practitioners fine tune. It is somewhere between 70 75 only. It's not a huge value you put in. Because the bigger this value is, the more change you will be doing. Smaller the value is, the less change you will be doing. That is one of the fine tuning parameters. So there are only two parameters: this KR and the occupancy. The occupancy. There are only two of them. It is basically for any unit change in the occupancy close to that one, how much variation you are actually accepting. Do you guys have any further question? I don't have any other question for the tutorial right now. That's what they specify. I mean, for the site. So this is a totally an engineer's judgment. There's a minimum I'm going to specify is that much. Imagine like this: you don't want to have a 3 minutes or 4 minutes green time or dead time, right? You might say I'm going to restrict it to let's say if you put 850, what does the headway in this case? Sorry, 4.23 is the header, but you have two lanes. It was 8 point something, right? So you're saying I'm going to restrict to 8 to 10 seconds only. So it is how long you're going to hold it. It can be 30 seconds. Is too long for the motorway. So you just specify I'm going to use the 8 seconds or 10 seconds or 12 seconds. So you might be increasing it in terms of seconds, and that seconds you bring it here.
with respect to the design of the
Yeah, this one
normally downstream occupancy measurement
will be
always higher.
no, it can be lower also. So when it was lower, if the downstream, then you're going to increase the meeting rate. If it was lower, then you start increasing it. So what,
32%
that is the real observation you are having from a downstream detector. So I showed you a plot where occupancy was changing. So that is the occupancy you are observing from a downstream, and this downstream means downstream of the merge area. If you remember, you remember what I was, yeah. Mhm. So it is always the downstream of the merge area.
the merge area is what?
Yeah, I'm just going to open the slide one. That's the one. So you have on ramp, you have a detector here, you have a detector there, right? So you try to use the occupancy here. If this thing fails, you can start using this as a proxy.
So 28
From here, only here, only this one. That's a 20-second occupancy. 20-second occupancy with the smoothing, exponential smoothing. You remember smoothing I discussed is not an individual value. So I think they use a 0.3 as one of the exponential smoothing one. So it is the smoothing that is also done in that case. So it's not the raw occupancy you are using. You're always smoothing the occupancy also. So what I meant by that's the one we discussed the yesterday. You might have a time series of your individual observations. You basically yeah, you apply an smoothing value on it. So instead of flow, think of the occupancy here now. So use, let's say 0.3 is what you have used. So 30% of the last observation plus 80% of the previous smoothened value. So you get the smoothened occupancy. Even the plots which I was showing, they were smoothened occupancy. They were not the actual occupancy. So normally it's up to, detection can be at 30 seconds, 20 seconds, 10, I mean, the aggregation. So normally they might be doing it every 20 seconds aggregation. The 20 means it will give you 3 observations in 1 minute, right? If you do it 1 minute observation, it will give you only 1 data points in 1 minute. So you will have more data points if you are doing a 20 second. There's no point of going below 20 seconds. It's too small time interval to get some meaningful value. But 20 will give you 3. So what we recommend is get your exponential smoothing done. Like you have 3 20-second one, aggregate the last 3 ones to get 1 minute one, but then do an exponential smoothing on it so that you have data points every 20 seconds, but they are smoothed over the last couple of times. So what happens is when you have a 20-second data, for example, there's a lot of fluctuation happening. So you get it your 20-second, you aggregate it over the last 3 ones in a rolling horizon. So if I have something right now at, let's say, 5 or 450, you do the last 3 ones, that will give you one value, and then you run the exponential smoothing over those last aggregated over the previous ones. Then you have a next 20-second, you have a new data, do another aggregation and do the smoothing. That's the way to go, because 20-second data will make you more efficient, or will make you more quick to make a decision. If you go for 1 minute, you have a lag of 1 minute to actually make a decision. But yeah, we apply the smoothing on it. Yeah. Yeah. Any further questions? You want to present? Yeah. Oh. Oh yes, you're right. Yes, yes. Then you cannot present. Yeah, I know that. Yeah. Okay. Further questions? But that is actually the one that you see here is quite different one. How do I show this? This one is, in Brisbane, we have, or in Queensland, we have like all the public transport vehicles equipped with the GPS, and you are getting the data almost every 10 seconds to 20 seconds. That's the real-time visualization of the entire public transport system in actually Queensland. We were having a chat for something, that's why this visualization was open. I will discuss about it tomorrow when I'm going to talk a bit about GTFL data set, but this one is just in terms of real-time visualization of the public transport. Yeah. Yes, you have that. Perfect. Mhm. Okay. That is the GTFL data set you're having, right? For the Guwahati buses, or only IT Guwahati? Okay. For us, okay, for you guys. But I mean, you have this GTFL data set available for, like, I know in Delhi you have it in Bangalore, you have it in Surat. There are actually various places you have it. Yeah. Is there any further question from the online audience? No. If not, then maybe we can end early today, and then we can start tomorrow at 9. Yeah, it's good.